welcome to the second lecture. If you were to look at, let us just go briefly through what we did in the last lecture. So, as I said, we are mainly concerned with what might be called high level programming languages, of which I said there are three kinds: imperative, functional, they are the most important, and logic itself can be used as a language. But our main concern was with these imperative and functional languages. They are also similar, so in certain respects. So, imperative languages are what might be called state based languages, where state updation is the main action, whereas functional languages are really value based languages, much closer to our mathematical languages. And the notion of variables in functional languages is very much like the notion of variables in mathematics, whereas the notion of variables in imperative languages is more like the quantities in physics which can change over time. Quantities like acceleration, velocity, and so state based languages means that there is a state change along let us say something like a time axis, though unlike physics we are not talking of continuous time, we are talking of discrete time. In the case of functional languages, the notion of a variable is really a variable in mathematics, which means that a variable just is a name for a value and it cannot change in time during the execution of a program. Anyway, so let me just briefly look at, so if we look at the history of languages, most of the work on high level languages is really concentrated on the imperative languages, and there are hundreds and hundreds of programming languages. So, firstly it is impossible to study all of them. Okay. And if you look at the history, you find that a large portion of the time during the 50s and the 60s, a large portion of the time was really concentrated on what might be called the basic features. So, which means these represent the basic control structures, the exploration of the basic control structures and the basic data structures in order to obtain clean, readable programs, efficiently implementable programs, efficient running programs, and so on. But later, once these things were fixed in the 70s and 80s, most of the exploration of programming languages was in terms of what might be called features. Like if you were to take modular, its most important feature, it is just an extension of Pascal, its most important feature is that of a module. If you were to take Ada, it combines the module features of modular and adds more features like concurrency as an important feature, exception handling, generics or polymorphism. If you were to take, so similarly Clue is a module based language very much like modular, but with a different syntax, but they are all extensions of Pascal in the sense that the basic control structures remain the same and then you extend the language. If you look at these, the basic control structures in these languages could be different too, they are not very similar, except that these arrow marks denote their descendancy in terms of the similarity of even the basic control structures. So, from similar, let us say even though the Smalltalk 80 control structures and syntax are different from that of similar, the basic extensional feature comes from a new feature of similar which was extended, and that is the notion of a class or objects. Okay. So, these so what we mean by features are these kinds of features, whether the language is sequential. Most of the languages in the early 60s was sequential, whether they are concurrent, whether they are modular, whether they are distributed, whether they are parallel, whether they are object oriented, and so on. Yeah. So and nowadays by and large the exploration is mostly in terms of new features, what kind of new features, and what I have listed as the various kinds of features is, let us say, the current state of art. A large amount of work is into trying to make them more efficient, trying to make them more readable, comprehensible, and so on. Okay. So, the basic functional languages also have this feature that the early functional languages were all an exploration of very basic data structures and controls and control structures. Then languages like ML and CAML actually signify the addition of new features. In fact, the syntax of ML expressions and so on is much closer to that of Pascal than, let us say, of Lisp, but philosophically it is a more Lisp like language because it is an applicative or a functional language. It is not a state based language, and it goes far beyond Lisp in the sense that there are new features like the introduction of modules, the introduction of exception handling, the introduction of very powerful data abstraction mechanisms, and type checking. Okay. So, Lisp has no type checking at all. Right. So, let us look at so we will first study the basic features of languages, and so let us look at what constitutes maybe what are the issues in something like language design. If you were to design a language, what kinds of issues would you really have to study, right? So, one very major issue that the implementation that the language Pascal has taught us is that it is a good idea, it is a very good idea for a language to have a simple, clear and a small set of unified primitives for expressing basically all your algorithms and data structures. One of the nicest things about Pascal, or in general about what are known as Algol 60 like languages, is that most algorithms are written in some crude variation of the dialect of Pascal or Algol 60, right. So, the nice thing about Pascal is that it is a small language, easily learnable, for example, which is why most people are taught Pascal initially. And so, one issue could be that you should start with a small language with a small set of primitive operations over which you can build. Yeah. And secondly, the next issue would be that you should have an absolutely clear syntax, there should be no ambiguity, and you should be able to get highly readable programs. It is very important to have readability. That means by readability it means that I have to be able to read the source code of the program like a book, and a very good reason for that is that no piece of software that you write is ever permanently fixed. What happens is that well, most pieces of software have bugs in them. So, bugs might be detected years and years after the software has been commissioned. So, what and years after means that there must be somebody else, if a bug is detected, who should be able to read the source code and be able to modify it. And in order to be able to read the source code, he should be able to understand the algorithms that the source code contain. So, in fact, efficiency and such considerations come much later. Readability is the most important thing because it includes maintainability of the software. Yeah. So, normally the person the person or persons who have written the software are not likely to be present to maintain the software. So, the software in general has to be maintained by somebody else. So which means that the source code must be readable. So that is first thing. The second thing is that over the years the software actually as more and more users use that piece of software, more and more users feel the need for its extension. So you have to be able to extend the software, maybe by adding new features, by adding some more conveniences, whatever may be the reason. So part of the maintainability of a piece of software is not just the detection and correction of bugs, but also the extensibility of the software. As the years go by and more needs are felt, it is necessary for somebody who is usually not the original programmer or the original team which wrote that software to be able to extend it, and for all that readability is most important. Yeah. And secondly, that a language should provide what is known as a support for abstraction. The basic abstraction mechanisms you are already aware of. The control abstractions are things like procedures, functions in Pascal, loops, loop statements. There are various kinds of control abstractions. There are also data abstractions, like for example the most primitive kind of data abstractions that Pascal provides are the record structure, of course arrays, which almost all languages, even the early languages had. So arrays are one data abstraction. That means you think of a whole sequence of elements as a single unit, and you try to as a single logical unit. So records, variant records, and of course what has been felt in later years is that you should have abstraction, data abstraction, which allows you not just the ability to take sets of data together as a single unit, but also to operate on them as a single unit. So combinations of operations and data abstraction in a module basis, okay, or further abstractions like you might require, I mean for example languages like ML, Ada provide the notion of a generic or polymorphism, where you can use types themselves as variables and change types and instantiate the same kinds of algorithms, for example stacks. It does not matter whether you are talking of a stack of integers, a stack of characters, a stack of reals, a stack of some complicated data element, maybe a stack of some record of things or stacks of arrays of things. The basic operations on stacks are like pop, push, checking for emptiness and so on. They should all be available in one form, and it should not be necessary for me to repeat the code depending on the type of element, right. So that is an abstraction where the basic element of the stack itself is a variable which can be instantiated to a different type each time, and I use the same piece of code, carefully written, verified, maybe thoroughly tested, and instantiate the type so that I get different kinds of stacks with the same kinds of operations on them, right. So the support for abstraction is an important modern language design issue, and other kinds of issues that have come up or which are becoming more and more reasonable is, one is that you should be able to verify your programs. So the language should also provide support for verification, provability of programs, not necessarily machine based provability, but possibly a hand based provability or a mixture or a user interactive provability of programs. And something that was felt even in the 60s and where a lot of time and effort was expended in the case of Fortran and COBOL compilers was portability, okay. Nowadays, so when I say portability, what it means is that the language design should be such, the language should be such that it is oriented towards an end user and is not architecture or or machine specific, simply because a certain machine has a certain kind of assembly instruction. It does not mean that you make that available in the language. Other machines may not have that. So so a machine independence means that you should be able to provide as far as possible an abstract form which is not related to the machine, okay, which uses only the basic instruction set which will be available in all machines. If you ensure that your language is really architecture or machine independent, in the sense that your main concerns have been are with the user's convenience, the abstractions required for the user, and are not specific to particular machine instruction sets or particular architectures. Like you might have register based architectures or stack based architectures. If you can design the language in such a fashion that it is not architecture specific or machine specific, then what it means is that I can move the entire language to another machine with a different architecture and with the minimum amount of effort. There are certain machine specific details which still have to be changed when I move an entire language implementation from one machine to another or from one architecture to another. But the whole idea of the language design or the design of its implementation should be that the amount of changes that have to be made should be minimal. So we will look at some reason for that. So and then there are things like you should be able to easily implement. I mean, you cannot compromise everything at the altar of portability, ease of implementation, the availability of ready algorithms for implementing the language should be a consideration. Ease of implementation was perhaps the most important reason for this, and the fact that it used very low level primitives is perhaps the most important reason for the success of the C language, for example. And well, efficiency is another important reason. C programs run very fast and they are very efficient, and something that if you have a language and you want it to be generally acceptable, then what it should have is a clear definition of what its constructs do, so that if it has to be widely acceptable, there might be many different implementers trying to implement it on various machines, and only if there is a common clear syntax, a common clear semantics or the specification of the effects of each language construct, each construct in the language, only then you can expect to get wide applicability. Okay, so we will get to the notion of semantics later. Then of course there has to be it has to be runtime efficient. By runtime efficient, I mean that the programs have to run efficiently. This is efficiency of the implementation, which means very often it means compile time efficiency. How fast can you compile programs written in the language? Whereas this runtime efficient is that it should have an excellent runtime support, and the program should run as fast as programs written in the language should run fast. Yeah. Ease of maintenance. Here I am talking about the maintenance of programs as well as the maintenance of the language by maintenance of the implementation of the language. There might be bugs in the language implementation, and fast compilation, translation, and support for extensibility, which is in fact the most important reason why, for example, Pascal is used as a basic support the language of Pascal is used as the basic language from which you add onto which you add new features to get newer languages. There is one controversial feature, that is a support for subsets. This used to be something that most programming languages books used to specify, that every language should support subsets of the language, in the sense that it should be necessary for me to use only a smaller set of operations or features of the language than is actually necessary. And you should, by support for subsets, what I am saying is it should be possible to take, you should be able to divide up the language so that there is a small kernel and larger and large sort of extensions. Okay. So that all programs written for the small kernel anyway run on all machines regardless of the subset supported. Okay. However, the language of Ada, for example, in the 80s has clearly specified that there should be no support for subsets, and their reason is that then it affects the portability of programs written in the language. Yeah. So support for subsets is a controversial thing, which it is not at all clear whether it is desirable, especially in the, as in the case of, I mean, the most important language for embedded systems, you know, real time things with systems that control sensors, various kinds of hardware, ballistic missiles and so on. It would affect their portability, because you would have some feature which is used in some implementation, and then you move the program to another implementation which does not support that feature, then your programs do not run, right. So the portability of actually programs written in the language gets affected if you allow arbitrary subsets. Yeah. Okay. So if you look at all these features, and so finally what we can do is, so, and then there are hundreds and hundreds of programming languages, it is impossible to study all of them, and what is more, it is not necessary. So what we would like to do is to divide up the study of programming languages into a few small parts. So what we will do is we will look at, so what does a theory of programming languages contain? Yeah. So a general theory of programming languages is based on three things. What might be the most important thing is, or the most basic thing is what is known as the syntax of the language. Okay. So a programming language is really like a very highly simplified natural language. It has a certain syntax, right. So which means that it has a certain, what might be called grammar. Certain things can occur only in certain ways. You cannot arbitrarily take, you cannot arbitrarily form sentences of the language. As I said, a program written in that language is just what might be called a sentence of the language. And like in a natural language, you take a sentence of a natural language, it has various parts. So for example, in almost all languages, all natural languages, one thing that any full sentence should have is a predicate. There is a, it has a syntactic category called predicates, okay, which in general may not be words. I mean, a predicate could be a clause or a phrase. So it might have a subject too. In addition, it might have an object. So if you take a sentence in natural language, so if I say run, that is a complete sentence because it has a predicate. No complete sentence in the natural language is without a predicate. Okay. So run is a complete sentence, it has a predicate. Optionally, it might have a subject, maybe also an object clause. So, and the subject clauses have to be of a grammatical form called, they must be subject phrases might be noun phrases, which means they might have nouns qualified by adjectives, maybe an article, and so on and so forth. Yeah. So what you can do is you can divide up any grammatically correct sentence in a natural language into firstly various clauses. Each clause may be into various phrases, and all those phrases have certain grammatical properties. Yeah, in very much a similar manner, in a greatly simplified form, are what you might call the parts of speech of a program. Yeah, so every programming language has a certain grammar which specifies various parts of speech. It has a certain what might be called vocabulary, and it is possible to take a sentence of this programming language and parse it. We will get into the meaning of these things more clearly later. But the similarities with natural language, after all, a lot of the theory of syntax was actually inspired by natural languages, by the construction of artificial languages which did not have a lot of problems with the natural language. Yeah. The next thing is what might be called the semantics. Very often the semantics of a programming language is really specified by its reference manual. So, if you in your in your study of Pascal programming, one of the important references would be the ISO standard Pascal reference manual by Jensen and Wirth. Okay. So, that reference manual really specifies for each syntactic entity of the language what is the effect to be expected by executing that syntactic entity. So, in other words, what we are saying is for each language construct, what are the meanings associated with it. Yeah. So, the notion of meanings is something we have to look at. Unlike natural language, the notion of meanings is something that can be specified mathematically in a machine independent fashion. So, when we are talking about the semantics of a programming language, we are talking about a pure meaning associated with the language regardless of any machine on which the language is implemented. In general, we are talking about meanings in an abstract setting, in the sense that you assume, if you like, for practical purposes, that you have no restrictions on word lengths, you have no restrictions on memory, you have no restrictions on computational power, except that you can only do a finite number of operations at any instant, right. So, you assume a sort of, so the programming language itself can be thought of as a mathematical entity quite independent from all its implementations. And in general, when you think of it that way, then what you are saying is you are thinking of some kind of an ideal machine which has no restrictions, except one restriction, that at any instant of time only a finite number of operations can be performed. I mean, you cannot do an infinite number of operations at an instant of time. So, if you consider such an ideal machine and then you are really looking at the programming language as a mathematical entity in some ideal environment. Okay. And the meanings of that, of the constructs of the language in that ideal environment, form what might be called the actual reference manual. So, if you were to go through the reference manual of Pascal, let us say, since that is one thing that you have all studied, there are certain, most of that reference manual is independent of any machine. There are certain machine specific paragraphs or what are known as implementation dependent features. But if you look at the language itself, it is capable of looking at the language as an entity devoid of any machine. Yeah. So, most of the time, so in general the semantics would follow the syntax the syntax has a certain structure which we will come to, and the semantics. So, the syntax has got some what might be called some basic elements and some compound forming operations, yeah, connectives, compound connectives which allow you to form compound let us say sentences from simpler ones. So, the meanings in general should be such that you give the meanings of the basic elements and then you give the meanings of the connectives in terms of the basic elements. So, very often, so what it should be necessary is, since a programming language is really a finitary object which allows you the construction of an infinite set of programs, okay. It is not possible to, unless you have this basic discipline that you express the effects of connectives in terms of the effects of the basic elements of the language, it is not in general possible to predict the behavior of the language, of a program written in the language, unless you follow this discipline. Okay. So, a basic feature of any kind of semantics is that it should allow for the derivation of the meanings of an infinite number of programs, which means the only way to derive the meaning of a program should be from the meanings of its finitary elements. So, you have certain basic elements from which complex elements are formed. So, the meaning of the complex element should be derivable in terms of the meanings of the basic elements and the meanings associated to the connectives which form the complex element from the basic elements. Okay. So, what it means is that semantics is going to be intimately related to the syntax. The syntax is really a way, a finitary way of specifying an infinite set of allowable objects. Okay. The infinite set of allowable objects are the programs of the language or the sentences of the language, and the syntax gives you a finitary mechanism for specifying all possible allowable programs, very much like your set theoretic notation, right, the set builder notation, which allows you to give a finitary specification of an infinitary set, of an infinite set. And so, the only thing that is really analyzable for an arbitrary program is its structure in terms of its syntax, the finitary specification. So, the meaning of the program has to be derived from its finitary specification, has to be expressed in terms of its finitary specification. Yeah. So, lastly, so this is the semantics of a language is in a sort of an ideal environment. Do not worry about machine constraints, do not worry about architecture, they are all, we do not want to worry about them, because for one important reason, I mean, the programs have to the programming language has to be portable. Okay. Do not worry about word lengths, do not worry about limits, do not worry about memory constraints, assume infinite amount of memory available. So, then what happens is that you get into what are known as pragmatic considerations. Yeah. So most of these implementation dependent features are really pragmatics. For example, the Pascal reference manual does not tell you how to associate a disk file with a file variable inside the program. That is one example of an implementation dependent feature which will vary depending upon the operating system interface you have. Yeah. Then there are various simple implementation. So, the pragmatics firstly involves really all the algorithms that are going to be used for the implementation of the language, all kinds of machine and architectural constraints. For example, the maxint, the maximum integer allowable in a Pascal program, is a typically implementation dependent feature, because it really depends upon word length or byte length, or whether it uses 2 bytes for representing integers and so on and so forth. right. So, the value of maxint can vary from machine to machine, the amount of memory that is available for a program can vary, whether it is a stack based machine or a register based machine, those things are implementation dependent features. Okay. So, normally what we would do is, even in our implementation, in order to make the language portable, we will separate out the basic algorithms of implementation from the architectural specific nature of the implementation. When we read through a small compiler, you will see this happening. So, there are certain basic algorithms which are really machine independent, and then there are some machine dependent features in the actual code. So, then you have things like the OS interface, what is the nature of input and output, whether it is file based, terminal based, sensor based, whatever, signal based, and the OS interface also includes the file server, how the language has to interact with the file server, with how the language has to interact in general with the directory service of the machine, and so on and so forth. And lastly, what is to be done about errors? And by errors I mean errors introduced by users in their programs. So, errors could be of a syntactic nature, errors could be of a runtime nature. What is to be done about these errors? As a blanket there is a blanket policy could be just that you just abort, but that does not help anybody. In particular, what is the nature of error reporting? Is there some error correction that can be done? Is there some way of recovering from errors, so that as soon as the first error comes you just throw out the program? No, it's if you can, at least you should be able to point out all the errors in the program or all possible things that are errors, so that the user gets to know all the errors at one time, and it reduces the amount of compilation effort. And similarly, and you can't do that at runtime maybe, but at least there should be some decent error reporting mechanism, some error handling mechanism. So, that is one thing, but errors is a very dicey object, it is a very dicey policy, and different languages have taken different attitudes, different implementations take different attitudes. So it's a very pragmatic feature. Yeah. So, I will just briefly go through the notion of syntax, and then maybe I will stop. So these are the three issues, and it is better to study all three issues sort of separately. The semantic and pragmatic issues will closely depend upon the syntax, and it is preferable that they depend upon the syntax. So, let us look at what constitutes syntax. Yeah. So, a syntax has to do with a form or a physical representation of possibly an abstract object. Yeah. So, if you look at numbers, numbers really are not very physical. At least the 20th century attitude towards numbers is that they are a conception of the mind and they are not physical. What they do have is a physical representation in the form of numerals. Okay. So, what you write out and think of as a number is actually a numeral, right. So, while you have various ways of representing the same number, let us say the number 126. So, you can have what is known as the positional representation, which is what we normally use, well, this is 126 written in hexadecimal, and I hope it is correct. Yeah. So, you might in the basic form, all these three representations of the number 126 are really the same. Okay. The Roman representation differs from the Devanagari representation in the sense that the characters used are different. What might be called the basic alphabet for the positional representation of numbers is different in the two. It is just that the character set is different. The character set is also different. It is a positional representation which uses a different base. The character set therefore is also different, but that is incidental. Yeah, but in their basic forms, all these are unified by the fact that they are all positional representations. Yeah, positional representations. I hope everybody understands that. I mean, right? You go in units, tens, hundreds. Here you go in units, 16s, 64s, and so on. Right? Then of course you have the Roman numerals, which is non-positional, which has, well, firstly it has a different alphabet. You could represent the same same number 126 with different character sets, but there is something unifying about this. There is something fundamentally different about this representation from any of these. Yeah. So, and what is it that is fundamentally different? If you disregard the change in character set, what makes these two the same? What makes these three the same? And what makes these three different from these two? Okay. What makes that what makes these two classes different is the grammar of the numeral, of the language used for representing the number. Yeah. In both these cases the grammar is actually exactly identical, the character sets are different, and by and large the grammar of all these three is the same except for the character sets, but the grammar of this is different from the grammar of this, in the sense that the form of representation is fundamentally different. How you represent compound forms from simpler forms is different between the Roman and the Arabic case. Okay. So what is that grammar is what we have to study. Yeah. So let us look at this in the more general setting of a programming language. So we might think of every programming language as having a vocabulary. Okay, a vocabulary is, well, what you might call a complete dictionary of words of the language. Okay, and a word of the language is formed from a character set, from a fixed character set, and, well, you identify certain strings of characters as words, as allowable words or part of the vocabulary of the language. So a complete dictionary of the language is what constitutes, let us say, its vocabulary. So if you look at, I mean, so what I am saying is, so if you take languages, for example natural languages like Konkani or Sindhi, what they have is different character sets, and but the same collection of words. Okay. Sindhi, for example, is written by different people. Some people write it in Devanagari, some people write it in the Urdu script, the Arabic script. Okay, but the collection of words is the same. So a person who knows Devanagari can communicate with a person who does not know Devanagari but knows the Urdu script by speech, because the words are the same, but you cannot communicate by letter. Okay. So there is a certain fixed collection of words whose actual form may depend on the character set, right. But given the words, there are what are known as formation rules. Yeah. So given a vocabulary, there are ways of combining words of the language to form sentences of the language, and there is a finite set of formation rules which are called, the formation rules are called productions, which allow you to generate all possible sentences in the language. So let us quickly go through one example. So we will not worry too much about this character set, because I think that's so for a programming language, for example, the character set really depends upon the kind of codes you use. Nowadays most of the time we use ASCII codes, but then we have 8-bit ASCIIs on PCs and 7-bit ASCIIs on mainframes, so the character sets are different. There are all these kinds of differences, okay, but let us disregard them, and let us just look at, so let us just look at what constitutes a grammar. So I would say, so a grammar is really a 4-tuple of objects, okay, where there is a set n which is called the set of non-terminals, and this set of non-terminals really specifies various kinds of grammatical categories of the language, like you might say the parts of speech: noun phrase, verb phrase, adjectival phrase, noun clauses, subject clauses, subject phrases, object clauses, predicates, and so on, okay. So this set n consists of the basic grammatical categories. All these sets are finite, okay. Then the terminal, then T is the set of what are known as terminal symbols or terminal words, and T is the complete vocabulary of the language, okay. So and P is the collection of formation rules, or what are known as productions, and S is what is called the start symbol, but S really represents a grammatical category in N called a sentence, yeah. So the basic element of the language is what constitutes a sentence, right. So let me just quickly go through, okay. So here is a simple grammar specifying Boolean expressions. So there is a start symbol S. Every grammar should have a start symbol S and some grammatical categories. The grammatical categories that I have chosen are A, V, and C, which actually stand for an AND Boolean expression, or an OR Boolean expression, or a complement Boolean expression, okay. The vocabulary of this language consists of all possible Boolean variables that you might take, the 2 left and right parentheses, and the 3 connectives AND, NOT, and OR, okay. These are the productions. From the start symbol, any Boolean variable is a Boolean expression. That you take any B belonging to this set of Boolean variables, that in itself is a Boolean expression. So the sentences of this language are Boolean expressions. Actually they have more than fully parenthesized Boolean expressions, okay. So a sentence is either the complement of a Boolean expression, or the OR of 2 Boolean expressions, or the AND of 2 Boolean expressions. An AND clause, if an AND expression is one of the form which consists of 2 Boolean expressions enclosed in parentheses and separated by the word AND, okay. An OR Boolean expression similarly is 2 Boolean expressions enclosed in parentheses and separated by an OR, and NOT is similarly this, yeah. So these productions are really replacement rules. So whenever you find an S, you can replace it either by an A, a V, a C, or one of the Boolean variables. Whenever you find an A, you have to replace it by this. There is no other way you can replace A by anything else. Similarly, whenever you see a C, you have to replace it by this. And so here is a simple sentence generated, right. So you start from S, and one of the possibilities is that you can replace S by C. Okay, whatever I am replacing I have circled in orange. So, you can replace S by C. C has to be replaced by something of this form, by this, and now I am replacing this S, leaving everything else intact. So, I have chosen here to replace S by A, and once I have once I have got an A there, the only possibility is to replace it by something of this form S and S. I have chosen to replace this S rather than this S first, and I have chosen to replace it by a Boolean variable. So, let us assume that there are only 2 Boolean variables B1 and B2, and I proceed in this fashion, and lastly I get a complete sentence of the language which consists of only the terminal symbols, and this is a sentence of the language generated by this grammar. Yeah. So, we talk of a language as being generated from a grammar as the set of all possible sentences that may be generated from the start symbol S. Important warnings are that the set of non-terminals and the set of terminal symbols are disjoint, and a production is really a replacement. It replaces a non-terminal by a string consisting of terminals or non-terminals. Yeah, and a sentence is just a string of terminal symbols generated from the start symbol. Yeah, so I think I will stop here now.